Special purpose PN junction diode. Okay. First one, that is Zener diode. Now see, Zener diode is named after its inventor. Okay. And the name of the scientist was C. Zener. So this diode is named as Zener diode. Symbol of Zener diode, that is exactly like the symbol of a PN junction diode, but a small change is made here. And see, this N-type semiconductor for PN junction diode, it is represented as simple line, but for Zener diode, it is represented as the letter Z. So here end of this line, that is slightly made in such a way that the letter Z is here, like that it looks. Okay. Now this one is the symbol of Zener diode. Now how the Zener diode is formed? So Zener diode is formed with the concentration of impurity atoms increased one. It implies that, see, in simple PN junction diode, the concentration of impurity atoms was considered 1 impurity atom per 10⁶ host atoms. Here, the concentration of impurity atom is increased. Now, due to this increase in the concentration of impurity atoms, what happens here? Now, if we carry out the study related to IV characteristic of PN junction diode, then forward bias characteristic is as it is, just like normal PN junction diode. But there is slight change in reverse bias characteristic. Here, the reverse breakdown voltage, that is called Zener voltage, and exactly at that voltage, all of a sudden, rapid increase in the current takes place. So here, current increases, see, like this, but the voltage that remains constant. Okay. Now see, depending on this particular characteristic, this reverse biased, we can use diode as voltage regulator. We can use diode as voltage regulator. And why this happens here? Exactly at the breakdown voltage, the change takes place. In normal PN junction diode, after breakdown voltage, small change in the voltage give rise to the current. But here exactly at the same voltage, you get rapid increase in the current. Means voltage remains constant, but current will be increased. Okay. And this one is due to increased concentration, because if we increase the concentration, then here, so here, due to increase in the concentration, the width of the depletion region decreases, as well as the electric field in the depletion region becomes stronger one. And due to that, at a particular reverse bias voltage, the electric field becomes sufficient strong so that large number of covalent bonds in the depletion region will be broken up and rapid increase in the current is obtained. But a very important thing, that is this one, current increases rapidly, but the voltage that remains constant across Zener voltage. Now see, here if this phenomenon takes place, then the reverse current which increases, that is due to flow of electrons from P to N and holes from N to P. Okay, and we already discussed this thing, that particular reverse bias voltage at which this happens, that is called Zener voltage, represented by VZ. And in this particular case, the electric field developed, that becomes of the order of 10 raised to 6 volt per meter. Okay. Now see here, this particular flow of electrons, or we can say this particular electric field which give you tremendous large number of free electrons and holes, that phenomenon is called field emission or field ionization. So remember this particular word. Now, depending on this particular reverse bias characteristic, we can use Zener diode as a voltage regulator. Now, Zener diode here will be used in reverse bias mode. Zener diode always used in reverse bias mode, because forward bias characteristic, that is exactly like simple PN junction diode. Now see here, the output voltage obtained in full wave rectifier, that is unregulated one. Unregulated one, it implies that in the output there are the components of AC, or in other words we can say the output obtained, that is not 100% pure DC. Now that unregulated voltage is given to the Zener. With Zener in series, one resistance is connected, and then after parallel to the Zener we have to connect the load resistance RL, and across two terminal of load resistance RL we will get the output regulated voltage. Now how it works? Suppose we want regulated output voltage that is equal to 6 volt. Then we have to take Zener diode with breakdown voltage equal to 6 volt. Now, as shown in the figure, we have to prepare the circuit. But to obtain output regulated 6 volt, the input unregulated voltage that should be greater than 6 volt. Suppose output voltage is greater than 6 volt, at the baseline of 7 volt there is some variation in output of the full wave rectifier, that is 7.5 to 6.5, 7.5 to 6.5, like that. Okay. Now here what happens, at 6 volt, this Zener diode, that will give you the rapid increase in the current. Now here what happens, across two terminal of the Zener, if the current increases in reverse bias mode, then also the voltage that remains constant. So here load resistance is parallel to Zener diode. So across load resistance also the voltage obtained, that will be 6 volt, because this is parallel combination. It implies that when the reverse current increases here through the Zener, and when it reaches at this particular junction, then limited current will flow through RL. so that it give you 6 volt across RL. And the rest part of the current will flow through this RS. So as per current into RS, we will get the remaining voltage drop across RS. It implies that suppose input voltage reaches to 7 volt. Here definitely 7 volt is greater than 6, so breakdown will take place. Current will increase, and now IL will flow through load resistance such that across RL we will get output 6 volt, and the rest part of the current will flow through resistance RS, so that current into RS that will be equal to 1 volt, and total between these two terminals, this one and this one, here across Zener 6 volt, across RS 1 volt, and total we will get 7 volt. So in this way, whatever the fluctuation takes place in the input unregulated voltage, corresponding to that, the potential difference will be obtained across RS. But the potential difference across Zener, that will remain constant, and that is 6 volt, and that will be obtained in output. So we can say output voltage, that is the constant voltage, equal to Zener breakdown voltage. And now we can say output voltage, that is regulated one, constant one. So in this way, Zener diode can be used as voltage regulator. Clear? चलो समझ पड़ी बच्चाने? Now see optoelectronic junction devices. The semiconductor diodes in which carriers are generated by photons, or we can say photo excitation. All these devices are called optoelectronic devices. Now there are 3 types of optoelectronic devices which we have to discuss here. One, that is photodiodes, used for detecting optical signals. Photodiodes convert light energy, or we can say photon energy, into electrical energy. Then light emitting diodes, in short, are called LED, which convert electrical energy into light energy. And third one are solar cells, which also convert the photon energy into electrical energy. Clear? Okay. Now, first of all, we have to discuss photodiode. Photodiode is a special purpose PN junction diode fabricated with transparent window which allow light to fall on the diode, right? And photodiode is always operated under reverse bias mode. Okay. Now when that particular diode is illuminated with light that is nothing but the bunch of photons, and we know this thing, if the light that is with frequency equal to F, then the energy of the photons, that is E, equal to HF. Now if this incidenting energy that is greater than the band gap energy of the semiconductor, then electron hole pairs are generated due to absorption of this energy by electrons. Because if this electron absorb this energy which is greater than band gap energy, then electron will be excited and transferred to the conduction band. So in this way, large number of electron hole pairs are generated. Okay. Now the diode is fabricated in such a way that the electron hole pairs takes place in or near the depletion region of the diode. Now we already studied this thing. There is the electric field at the junction. There is the electric field at the junction, and the direction of this electric field is such that the electrons will experience the force towards n-type semiconductor and holes will experience the force towards p-type semiconductor. So resultantly, electrons will be moved towards n-type semiconductors and holes will be moved towards p-type semiconductor. Okay. Now, due to deposition of electrons on n side and excess holes on p side, so that deficiency of electrons. So here potential difference will be developed between n-type and p-type semiconductor, or we can say end of the p-n junction diode. Now, if this particular diode is connected with resistance in the outer circuit and it is kept at reverse bias, then the current will flow in the outer circuit. This micro emitter will show you the current. So we can say if the current is constituted in outer circuit, means due to incidence of light, here the electrons holes are migrated towards n and p type semiconductor respectively, and the current is constituted. Okay. So if light incident, then only this thing happens. So we can say photodiode detect the light. Clear to all of you? Now its IV characteristic, that is as shown in the figure in third quadrant, we have to represent it, because photodiode is always operated in reverse bias mode. So photodiode can detect optical signal. Clear to all of you? Now solar cell. Solar cell, that is also a PN junction diode which generate EMF when solar radiation falls on the PN junction. It implies that the function of this one, that is like photodiode. Okay. So we can say photodiode and solar cell both works on the same principle. When light incident on it, it generate EMF. Okay. But photodiode, that is always operated in reverse bias mode, but solar cell does not require any biasing because itself give you some EMF, or we can say electrical energy or power. Now a solar cell is shown in this figure. See the construction of it. A p-type silicon wafer of about 300 micrometer is taken over, which a thin layer of 0.3 micrometer of n-type silicon is grown on one side by diffusion process. The other side of p-type silicon semiconductor is coated with metal, that is back contact. This one is p-type semiconductor and this one is back contact. Metal નું coating હોય છે, અહીંયા નીચે આ બતાવ્યું તે. Okay. Then after, on the top of n-type silicon layer, this one is n-type silicon layer, and on the top of it, metal finger electrode is deposited. This acts as front contact. The metallic grid occupy only very small fraction of cell area, so that when light incident on this one, then it properly enter to the junction diode. Okay. Now, when light falls on it, at that time, the generation of EMF takes place by three processes. One, that is the generation, second is called separation, and third is called collection. Generation means the generation of electron-hole pairs. Then electrons and holes are separated and then collected by electrodes. Okay. Now see, generation of EH pairs due to light, which one is incidenting on solar cell with energy greater than band gap energy, okay, close to the junction. Then second process, separation of electrons and holes due to electric field on the depletion region. Electrons are swept to N side and holes are swept to P side. And this electron reaching on N side are collected by front contact made by that metallic finger grid type electrode. Okay. And holes reaching P side are connected by back contact. Okay. So now here the front contact that will be negative, back contact that will be positive. So potential difference will be generated here. Now, if this front and back contact, right, which are electrodes after all. So between these two in outer circuit, if the resistance is connected, then from P type semiconductor means from back contact to N type semiconductor means front contact, the current will be constituted. Okay. Now, IV characteristic of solar cell is drawn in the fourth quadrant here. This is because the solar cell does not draw current but supplies the same to the load. Now, semiconductors with band gap close to 1.5 electron volt are ideal materials for solar cell fabrication. Solar cells are made with semiconductors like silicon, gallium arsenide, CDTE, and CuLnSc2. See here, band gap energies of all are given to you. So, here the important criteria for the selection of material for solar cell fabrication are band gap that should be in the range 1 to 1.8 electron volt. It should have high optical absorption that should be of the range of 10⁴ per centimeter. Electrical conductivity, availability of raw material, and cost. Here, one thing that you have to keep in your mind, sunlight is not always required for the solar cell to generate electric power, right? If sunlight is not there, but the radiations which are in the atmosphere incidenting on the solar cell are with energy greater than band gap energy, then the EMF will be generated. Okay. Solar cells are used to power electronic devices in satellites and space vehicles, and also as power supply to some calculators. Production of low-cost voltaic cells for large-scale solar energy is a topic of research that you have to do. Clear to all of you?